Hi, good day, one and all. Welcome to the HESA e-library, also called the HESA Video Bank. This video is being made to explain the concept of electrolytic conductivity. The only caution is that this video is supplementary material, not an alternate material to what we have in class. Right, so we start. Conductimetry. Now we are seeing that conductimetric analysis is based on the electrical property of ions in solution. Water as a solvent tends to encourage the existence of electrically charged particles. The conductivity of aqueous solutions and the information derived from the studies of immense importance in pharmaceutical chemists. The rate of movement or migration of ions in solution is dependent on a number of factors. So now, what brings about the conductimetry as we are studying this topic is the ability of solutions to conduct electricity. Now, that ability of solutions is because of the presence of ions. Then we have stated emphatically that some solvents like water encourage the existence of ions in solution. And these ions, just as we have electrons moving in metals, can also move to facilitate the transfer of electricity. Right? That is what we are talking about when we talk about conductimetry. Now, these are factors that affect the migration of these ions. The first one is degree of solvation. Now, the picture here shows us the degree of solvation. And so we are seeing that metal ions like sodium do not exist in isolation in solution. In solution, actually, you realize that it is surrounded by a water molecule. Now, if the solvation of the ion is heavy, right, this particular type of solvation is called hydration because water is around it. Solvation just means a solvent surrounding the ion, right? So this form of hydration, right, reduce the mobility or the movement or migration of the ion. Now, temperature generally will increase the migration of ion. Viscosity, if the medium is more viscous, it reduces the migration of the ion. The concentration is very tricky. The concentration, the number of ions per unit volume, generally the concentration is supposed to increase the conductivity, but because of ionic interference, it decreases the equivalent and molar conductivity. Now, ionic charge, the idea is that this one, we don't just look at the ionic charge, we look at the ionic charge together with the hydrated ion charge, right? So a simple example is that we can have something like sodium, right? Sodium, if you compare sodium to, let me write here, so lithium. Now, lithium has a smaller size compared to sodium. Generally, lithium should move faster. But in solution, lithium is more hydrated with water molecules. It's more hydrated. And so you realize that the hydrated ionic side of lithium, because of the high charge density of this one, is bigger. So lithium becomes bulkier and then it moves slower. And so that is, so we talk about the charge density. We relate the charge density to the hydration, the level of hydration around the compound. Right, so we look at the size of the hydrated ion. And if it's heavily hydrated, as we have lithium compared to sodium, we will decrease the migration of ions in solution. The last one is potential difference, and it goes that the higher the potential difference, the higher the movement of ions. Now we are saying solutions also obeys Ohm's law. The Ohm's law states that V is equal to IR. V is equal to IR, right? Now, specific conductivity. The conductance of a solution is the reciprocal of the resistance, right? And the specific conductivity is the reciprocal of the specific resistance. So, mathematical relationship for us to take note of. And whilst we take note of these, we have to also take note of the units of these quantities, right? Now, the conductivity or conductance is a measure of ease of current flow through a solution. The conductance of solution is measured using conductivity bridge, right, which we will do in the laboratory. That will be captured in another video. And when we talk about specific resistance of a solution, we are looking at resistance between two faces of a solution, 1 centimeter in width and 1 centimeter cross-sectional area. Now, this definition, we don't have to chew it. What we use to define is, if we know that resistance is directly proportional to the length and inversely proportional to area, surface area, right? And so what we do is that we introduce an equal sign and bring a constant. So when I bring the equal sign, the constant introduced is resistivity. Then I have my L over A, right? For me to define resistivity, I would assume the L is equal to 1. Then the A is also equal to 1, such that if I put 1 over 1 here, R is equal to P, 1 over 1. 1 over 1 is 1. So now the resistivity here will be equal to the resistance. So we see the specific resistance or resistivity is the resistance when we have for a solution, right? The distance between the electrodes, the two electrodes is 1 centimeter, and the cross-sectional area of the electrode is also what? Is 1 centimeter cross-sectional area. So that is how we define our term. Moving on. Right, so moving on, we say since E and L are constant for a given cell, we can combine it to give the cell constant. So instead of having the L over E, we can replace it with K so that we can have resistance is equal to cell constant times resistivity. Now we are saying the cell constant of a conductimeter is given by a ratio of the length over the cross-sectional area. It could be calculated from the dimensions of the electrode, but it is normally calculated accurately from measurement of conductance of a known concentration of KCl solution whose resistivity is known. The cell constant has a unit of per centimeter. Very simple. So we are done with everything around the cell constant. We will do some calculations later in the slide. Now we are introducing ourselves to a new concept called equivalent conductivity. Now the equivalent conductivity or molar conductivity, which are two different terms, is the conductivity K of 1 centimeter cube or 1 ml of solution containing 1 gram equivalent of solution. Now where the equivalent is coming from is the normality statement here, the 1 gram equivalent of solute, right? The 1 gram equivalent of solute is what's introducing the equivalent here. Now, if we are looking at molar conductivity, then we look at 1 mole of a solute, right? Now, this is the general formula for equivalent conductivity. We can simplify the formula to equivalent conductivity is equal to kV, right? Where V is measured in mils. V is measured in mils. Very important for us to keep this particular formula. We have to keep this particular formula. Now, an exercise for us to try our hands on. Very simple exercise. The specific resistance of 0.2 molar KCl solution is 361. And the conductivity cell containing such a solution has a resistance of 550 ohms. Calculate the cell constant. So this is a very simple one. And we have the resistance being equal to cell constant times the resistivity. The resistivity has been given here. That's the specific resistance. The conductivity was given, right? They didn't give us the resistance has been given. This is the resistance instead. The resistance has been given 550 ohms. So we just put the 550 here, we put the resistivity, and then we can do change of subject to get our answer. Now, when we get the cell constant is similar for the same cell, right? So we are saying if the same cell is filled with 0.1 molar zinc sulfate solution with a resistance of 72 ohms, what is the specific conductivity? So what we can do is that we can first of all find the specific resistivity and then use that to find our specific conductivity, right? So we have R is equal to K P, right? So the R for this one is 72 ohms. The K would have been gotten from that. The cell content would have been gotten from here. So we can find our resistivity when we are done. Then we would have the K, which is the specific conductivity equal to 1 over resistivity. And that should give us our answer. The question has been solved here. All right, so this is the answer. We can go through the answer. Very simple. Now, electrolytic conduction in solution. Solutions obey Ohm's law like metals, except under abnormal conditions such as very high voltage or very high frequency currents. The laws governing the electrolytic conduction of solutions are called the Faraday laws. Now, Faraday's first law. Faraday gives us two laws. We'll talk about the laws and how we can apply them in our discussion. The first law says that the weight of substance deposited or dissolved or liberated at the electrode during electrolysis is proportional to the quantity of electricity passed through. In mathematical terms, we say Q is equal to IT. The Q is for the quantity of electricity in coulomb, the I is current, and the T is time, right? Now, the second Faraday law, which we would solve questions on, states that when the same quantity of electricity is passed through solutions of different electrolyte, the weight of substance liberated at the electrode are in ratio of their equivalent weight. Now, in other words, we can also state that the amount of different substance deposited or dissolved by the same quantity of electricity are proportional to their chemical equivalent weight. In mathematical terms, we are saying that weight of A, if we are passing the same electricity through the medium, then the weight of A compared to the weight of B is in ratio of the equivalent weight of A compared to the equivalent weight of B. We have been given a very simple question to try respect to the second law so that it can enhance our understanding of the second law. It states that 1 gram of silver is liberated by 100 coulombs at the electrode. What is the weight of copper that will be liberated by the same quantity of electricity? So the same quantity of electricity commits the whole thing to the second law, right? Yes. Now we are saying, according to the general formula, we are just saying that the weight of silver, right, deposited over the weight of copper deposited is in ratio of the equivalent weight of silver all over the equivalent weight of what? Copper, right? And so if we are substituting, that means 1 over equivalent with the weight of copper deposited is equal to the equivalent weight of silver, which has been shown 107.88 all over 31.78. Then we can just do change of subject, make this one the subject and solve the question. So we have the solution here. Very simple. This is the solution. Very simple. Theory of conduction in solution, ionic theory. An electrolyte is any compound which in solution or molten state conducts electricity and can be decomposed by it. Two types of electrolytes are considered. We have the strong electrolyte and the weak electrolyte. Right? For strong electrolyte, there's always complete ionization, implying that the degree of ionization is 1. This results of conductor measurement shows that equivalent conductance and hence the conducting power of ions increase with decreasing concentration. That's with dilution for both strong and weak. Let me explain this statement. So for strong and weak electrolytes, right, they will dissociate to produce ions in solution. That will result in what? That will result in them being able to conduct electricity. Now, the nature of strong electrolytes is that they completely ionize in solution. But the fact that they have completely ionized in solution does not mean they completely dissociate in solution, right? There's some ionic interaction that exists, right? And so what happens is that because of that ionic interaction, in real instances, not all the ions are mobile to conduct electricity. Some of the ions still interact. Even though they are ionized, they will still be interacting because of electrostatic attraction. But then when you dilute it, you reduce that interionic interaction between the ions such that the conductance can increase. When you do that for a strong electrolyte, the value increases, but it tends towards a constant value. But then when you do that for a weak electrolyte, because weak electrolyte is characterized by partial dissociation, upon dilution, apart from preventing the ionic interference, it allows more of the electrolyte to also dissociate. Now, once more of the weak electrolyte is dissociating, the conductance is increasing. So dilution affects weak electrolytes to a higher extent than strong electrolytes, right? Because for weak electrolyte, dilution would increase the dissociation itself, so really affecting the conductivity. But in both instances, right, whether weak or strong electrolyte, dilution would increase conductivity, equivalent conductivity. For weak electrolyte, only a fraction of molecule ionize in solution, giving rise to low conductivity. But as dilution increases, the degree of ionization increases until infinite dilution, where there's complete ionization. In the case of strong electrolyte, there's already complete ionization at all concentration, but at high concentration, the ionic interference limits the movement of ions. I've already talked about it. Therefore, as dilution increases, there is less ionic interference, leading to increase in conductance. Now, inter-ionic attraction theory by Debye and Huckel. So two different people give us a better way to represent this interaction, right? They give us an equation. We'll not talk about this equation here, but they give us a criteria for us to actually estimate the actual mobile ions in solution that will be responsible for the reactivity or the property of that solution. And that is what Debye-Huckel did. So let's read. Now, the inter-ionic attraction theory postulated by Debye-Huckel gives explanation as to why the equivalent conductance of electrolyte decreases with increasing concentration. It states that oppositely charged ions surrounding a specific ion, that's ionic atmosphere, tends to move in opposite direction to the central ion, thereby decreasing the tendency. Now, if this is too much of English, we can look at what has been represented here. And so we have an atom of sodium here. We have sodium here. Now, sodium is positively charged. In solution, it will be surrounded by a negatively charged species, in this case, chlorine, right? So the chlorine surrounding it is its ionic atmosphere. This is the central atom, and this is the ionic atmosphere, right? Now, what happens is that when the sodium is moving to this direction, the chlorine will move to the opposite direction. So it will decrease the mobility of this one. It will interfere with the mobility of this one. That's not the only thing. Now, because of the presence of negative charge around this, it decreases the extent of positivity of this one by nets. So if we consider it in nets, you realize that the positivity of the sodium has been decreased because of the environment, the ionic environment. We call it ionic shielding. It shields the species, right? So the next thing that I've written here is that in the immediate neighbor of a positive ion, there tend to be more negative ions than positive and vice versa, right? You realize that in this positive, around this negative too, there are more positive around it. Positive ions are surrounding it, right? And so what we are saying is that arrangement of ions in solutions are not random. Positive ions will be surrounded by negative ions. Negative ions will be surrounded by positive ions. And because of this ionic interaction, it decreases the mobility of ions. Decrease the mobility of ions. Very important to note. Now, the Debye-Huckel theory, mathematical relation is given by, so this is the equivalent conductance equal to the conductance at infinity minus alpha. Alpha is a constant that has to do with temperature and the dielectric constant of the solvent, and C is concentration, right? Now, equivalent conductance at infinite dilution. This is a very important concept that we have to understand, especially for weak electrolytes. Now, we are saying that as concentration approaches zero, the molar or equivalent conductivity approaches an infinite value, which is practically a limiting value. It is known as the equivalent conductivity at infinity. It is presumed to be a measure of the conducting power of 1 gram equivalent of the electrolyte when it is split up into ions. And the ions are so far apart that there is no influence. And so let me explain whatever I've read here if it's too much English. What we are saying is that for both strong and weak electrolytes, there's some level of ionization. For strong electrolyte, there's complete ionization. For weak electrolyte, there's partial ionization. Now, when you start, let me write this equation, CH3COA, this is a weak electrolyte plus water. There's a reversible reaction. I would have CH3COO minus plus H3O plus. Now, as you are adding more water, the equilibrium is shifting to reduce the water. Equilibrium is shifting towards the forward reaction, right? Such that there's more dissociation of this one to produce the acetate ions, right? That is what happens. Now, as you add more water, more dissociation will happen. Now, once more water is also being added, it's reduce the ionic interference between this positive charge and this negative species, right? So we say we can continue adding water to a point of infinity where there will be no interaction. There will be no interaction. At that same point of infinity, it means the concentration is also approaching zero, right? Where there will not be any interaction at all. And this is where you can actually get the greatest equivalent conductance. We call that conductance equivalent conductance at infinity, at infinite dilution. Equivalent conductance at infinite dilution. Right? That is when you finally dilute. Now, for weak electrolyte, that will be the point where we would have complete dissociation and then zero ionic interaction, right? That's the maximum. As a maximum, that is where the maximum equivalent conductance can be measured, right? The conductance can be measured. Now, for strong electrolyte, because it's completely ionized, the equivalent conductance at infinity can easily be determined from the graph by doing extrapolation. But for weak electrolytes, because you need a lot of water, right? A lot of water, it is actually very difficult to determine it on the graph. Very, very difficult to determine on the graph because it always tapers on. It doesn't really touch the graph because it's a curve. Gives you a curve, right? Which doesn't touch the graph. And so we do calculation. We use a formula that we call the Kohlrausch's law to do a calculation to theoretically predict the equivalent conductance at infinity for weak electrolytes. Right? We'll talk about that in the subsequent discussion. So we are saying that the equivalent conductance at infinity for strong electrolyte can be obtained from a graph of concentration, of equivalent conductance against dilution or equivalent conductance against square root of concentration. Right? Now, the equivalent conductance for strong electrolyte is more markedly affected by dilution than that of weak electrolyte. The equivalent conductance reaches a maximum at a comparatively low dilution for strong electrolytes. Because the strong electrolyte is completely ionized, right? So low dilution can make it reach equivalent conductance at infinity, the maximum. Now, for weak electrolyte, the dilution required to reach the maximum may be impractical or impossible to measure. So this is the graph. You realize that the weak electrolyte does not really touch the graph. It's a curve, right? It's a curve. But the strong one is directly pointing to the graph. So when you do a direct extrapolation, you can just find the equivalent conductance at infinity. So with the graph, it's easier for you to find that for what a strong electrolyte. But for weak electrolyte, it's difficult for you to use the graph. So what we do is we use the Kohlrausch law, which we'll talk about. Now, these are equivalent conductance for some ions measured at infinity, right? Now, for cations, the cation that has the highest conductivity is H plus. For the anion, the one that has the highest conductivity is OH minus, right? Yes. Now we need this knowledge because when we are talking about titrations, we'll see how the graph behaves, and it's because of some of these things. It said that if the solution is removing H plus and adding sodium, because sodium has a lower conductivity, you realize that the overall conductivity will be decreasing. We'll talk about that more in the other discussion. So we have come to the Kohlrausch's law. Now, the Kohlrausch's law, the importance is that it will help us determine the equivalent conductance at infinity for weak electrolytes because it's very difficult for us to determine from the graph. So we are saying that when the equivalent conductance at infinity of a pair of salts having common ions are examined, certain regularities are observed. So this is the observation from which the Kohlrausch's law is gotten from. Now, KCl is 130.0. NaCl is 108.9. The difference is 21.1. Now when KNO3, right, and then the NaNO3, when we find the equivalent conductance at infinity, they are all strong electrolyte, and then we find the difference is 21.1. Now we have potassium sulfate, sodium sulfate, and we find the difference between the equivalent conductance and infinity. It is 21.1. Now the difference between these species, the anions in both all the instances are the same. The difference are the cations. So this is chlorine. Now calcium here, and this is sodium, right? That means, and that is giving you 21. The second instance too, the anion is the same, but the cation is calcium and sodium once again, and you're getting 21, right? Now the last one is sulfate, common sulfate. The difference is calcium and then the sodium, and you're getting 21. That means this difference is as a result of the difference in conductivity between the potassium and the sodium. That is what's accounted. That is where we got the idea from. So we are saying this shows the difference in equivalent conductance of sodium and potassium salt of the same anion as independent of the nature of the anion. This phenomenon is the basis for the Kohlrausch's law of independent migration of ions. Now, the Kohlrausch's law, you have to be able to state the Kohlrausch's law. Very important. It states that the equivalent conductance at infinite dilution of an electrolyte is equal to the sum of the ionic morbidities of the ions produced by the electrolytes. Let me repeat. It says that the equivalence conductance at infinity, at infinite dilution of an electrolyte is equal to the sum of the ionic morbidities of the ions produced by the electrolytes. Now, before I explain it, let's read the next point. So it is strictly true at infinite dilution where there's no mutual ionic interaction. So Kohlrausch is just saying that if we want to find the equivalent conductance at infinite dilution for, let's say, sodium chloride, right? This is a common example, very simple. We can add the ionic mobility for sodium and that of chlorine, and that should give us the equivalent conductance at infinity, at infinite dilution for sodium chloride, right? So we'll do a lot of examples to show. That is just what he's saying. With the equivalent conductance at infinite dilution of an electrolyte is equal to the sum of the ionic mobilities of the ions produced by that electrolyte. Very simple, very simple. That is what the Kohlrausch's law is saying in simple terms. Now, Kohlrausch's law. So the equivalent conductance at infinite dilution is equal to the ionic mobility of the cations and the anions. So this is a mathematical way of saying the Kohlrausch's law, right? Now, the importance of the law. And after learning how to state the law, this is the importance of the law. The law provides an important method for determining the equivalent conductance for weak electrolytes. Very important to note. Now, determining, so now this is practical application of what they are supposed to. And so this is a very simple example. We want to determine the equivalent conductance at infinity for, this is acetic acid, right? Acetic acid. But then, in this particular case, we have been given HCl. We have been given NaOH, sorry, sodium acetate, right? Now, when you add the HCl and then this one, you realize that you need the acetate from the sodium acetate here. You need the H from the HCl here, but you don't need the chlorine here and the sodium here because it's not part of this compound. And so you come and subtract the equivalent conductance at infinity of sodium chloride from it, such that by net, if I'm using the ions, this chlorine, the plus of the chlorine here will cancel the chlorine here, right? The negative of the sodium will cancel the negative of the sodium, so that we can have the addition by net. We'll just have the addition of the ionic mobilities of the hydrogen and then the acetate. The truth is that we will not give you the ionic mobilities directly, so we'll give it to you as a salt. And so you have to be able to manipulate so that you can get all the required salt and then remove the spectator salt or spectator ions from it. Right? We'll solve examples so we understand them more when we go down there. So this is an exercise for us to try. The answer is in the slide, so let's just know how we go about it. Now, the first one is for us to form formic acid. Formic acid. It's either you know how to draw formic acid, which is like this, or even if you don't know how to draw formic acid, right? You have formate here, formate plus a hydrogen, right? It's formic acid. That is it. This is it. That's how it is. Formate plus. So if you cannot draw, you can use this, but this is not the right way. This is for if you cannot draw it, but this is the right way, right? Now, if I want to form formic acid, I need in solution, formic acid will produce H plus, right? And then the formate ion, COH minus. No, let me redraw it. This is not right. So you produce H plus, right? And then it will produce H, COO minus, right? These two ions. So I need a species that contains H plus. Now I'll come and look at the salt they have given me. HCl has H plus for us, so I can take HCl, right? I need another species that contains the formate ion. The sodium formate here contains the formate ion, right? Now, if I add the HCl and then the sodium formate, I don't need the sodium here. I don't need the chlorine here. And so I have to find a single salt that contains both the sodium and the chlorine, so that when I remove it, I'll get rid of this and then this. So that will be the sodium chloride. So for me to form my formic acid, it will be the HCl plus the sodium formate minus NaCl. And that should give me the equivalent conductor at infinity for the formic acid. Now, if I'm looking at ammonium hydroxide, first of all, I need ammonium. The ammonium chloride here contains ammonium, so I'll take it. I need a hydroxide. Now, the sodium hydroxide here contains hydroxide ion, so I'll take it. Right? I'll take that sodium hydroxide. But then I don't need, in the ammonium hydroxide that I'm forming, I don't need sodium. I don't need chlorine. So these two salts, I'll add them and then subtract sodium chloride from it so that this sodium here can get rid of this sodium here. The chlorine here can get rid of this chlorine here, right? In order for me to get my ammonium hydroxide. So that is how it proceeds. Very simple. Very simple. We don't have to worry our head a lot over that. So this is the representation. This is how we represent our work. Ammonium chloride plus the sodium hydroxide minus sodium chloride. Then we get the ionic morbidities, right? If we separate them into their ions, you realize that the sodium here would remove the sodium here, the chlorine here will remove the chlorine here, so that we can get this. Now, this step is important because this is actually the step of Kohlrausch. This is actually the steps of Kohlrausch. So you follow these same steps when you are presenting your answer. By net, you just add the value for ammonium chloride value to the value of sodium hydroxide and subtract that of the sodium chloride from it. That is that for that. Degree of ionization. Now for weak electrolytes, degree of ionization alpha is given by alpha is equal to the equivalent conductance at any volume over the equivalent conductance at infinity, right? So equivalent conductivity at a specific dilution of volume over the equivalent conductance at infinity. We didn't see for strong electrolyte because for strong electrolyte, the degree of ionization is 1. Now, if we remember that the equivalent conductivity is equal to kV, right? kV. V is measured in mils, right? V is measured in mils. There's a question here for us to try, a very simple question. The specific conductivity of formic acid at dilution of 8 liters. Now, because of the formula we are about to use, you have to change the liters to milliliters because the kV here, the V is in mils, right? So, but the specific conductivity is, that's the K. The K is 0.0238 per ohm per centimeter. Now, they are asking us to find the degree of ionization. What we have to find, first of all, is the kV, right? The kV. We have the equivalent conductivity of V is equal to kV. Now, K has been given here. The V has been given, but it has been given in the wrong unit. right? It has given me 8 liters. We have to change it to milliliters. That will be 8,000 milliliters. 8,000 milliliters. So we just multiply 8,000 milliliters by this one, and that will give us our equivalent conductance. Equivalent conductance. Now, once we get our equivalent conductance, for us to find our degree of ionization will be the equivalent conductance, equivalent conductance over the conductance at infinite dilution, which has also been provided for us here. And that should give us our final answer. And it has been illustrated here. That is what has been illustrated here. Very simple. Now, titrations. Most of these ones will be done in the lab in another video, so you don't have to worry. But just for understanding, so you just rush through this one, right? So we are saying that changes in conductivity of a solution that occurs during a titration is made use to determine the equivalent point of reactions involving neutralization or precipitation. For ideal situation, two straight lines intersect at the equivalent point, right? But due to hydrolysis, this is a very important point in the lab. You will need it. Due to hydrolysis, dissociation or solubility of the reaction product at the region of equivalence point, the graph shows a curvature instead of the ideal clear intersection of the straight lines. I will show the graphs with a specific example. The first one, a strong acid versus a strong base. Now, for strong acid versus strong base, this is how it starts. Usually, we put the acid in the measuring cylinder or the conical flask, right? We use the conical flask for titration too. In the conical flask, sometimes some people use beaker lab, but let's use the conical flask. So, initially, we are plotting the conductivity or the conductance against the volume, right? This is volume. When you are plotting the conductance against the volume we are adding will be the volume of the base, and then what will be here will be the conductance, right? Now, for a strong acid in like HCl in the conical flask, right? The conductivity is high, so we start from a very high value. As we start adding the base, the NaOH, the value will decrease because the H plus ions is being reacted with the OH minus ions. So the H plus ions is reducing, right? And it's being replaced by the sodium ions. And so it will reduce up to a point, right? Now, at the base of you get a small curvature, and then it would increase again. Now, it's reducing shows when the H plus is being reduced by the OH minus, right? When it gets to this curvature, that is where we are getting to our equivalent point, right? Now, the equivalent point is ideally supposed to be a very sharp point, but because of the factors, the dissociation and solubility that we talked about up there, you get a curvature, right? So if you want to get the actual value, you have to extrapolate these straight lines and then draw from here to here to get the equivalent point, right? The volume of the base that neutralize the acid, right? Now, this point doesn't get to 0 on the bar because even at this point, when there's no H plus in the medium, when we just have water, there's sodium plus and then chlorine minus ions, which are still conducting, right? Now, there's a rise after the equivalent point because OH minus ions becomes in excess, and then it also has higher conductivity. That is why it goes back. So this is the nature of graph that you get for a strong acid, strong base, conductimetric titration. Conductimetric titration. The next one, we have a weak acid, strong base. Now, for a weak acid, strong base, this is what we will get. We are looking at the same graph, and this is concentration against the volume of base, right? Now, if we have a weak acid, it means it will start from a very small value like this. So weak acid, we have it low, not as high as we had a strong acid, very low. Now, when we start adding the base, it will reduce the H plus. And so you realize that it goes down a little bit, but it starts coming up. It goes down some small depression and then start coming up. It starts coming up because the sodium hydroxide here would force the partially dissociated acetic acid to dissociate more to give more H plus in solution. So you realize that even though the reaction is proceeding, the conductance is increasing small, and acetate ions are also being produced, increasing small. So a point where we get to the equivalent point, this, and then the OH starts becoming excess, where there's a sharp increase. No, this sharp increase is too sharp. Let me reduce it. Where there's a sharp increase, like this. So between the point where there's a steep increase and then the point where there's a sharp increase, between that point, we trace it to the baseline, and then we get what? We get our equivalent point. So this is the nature of the graph of a weak acid strong base conductimetric graph. Now, if we have a strong acid weak base will start like this. So strong acid weak base, the same graph, conductance here, volume of base here. Now, it's a strong acid, so we'll start from up here, very strong, right? Now, as we are adding the base, the A will be dropping, the conductivity will be dropping, right? To a point where we reach our equivalence point. Now, when we cross the equivalence point, you will not get a sharp increase, but you get what? Because it's a weak base coming, you get only a slight increase, Now, when you trade this point to the graph, you get your equivalent point. So this is the nature of a strong acid weak base. Now, for a weak acid weak base, it's very difficult because the changes are not really very steep. They are not very clear. They are just subtle changes. So concentration against volume. We have a weak acid, so it starts very slow. It depresses initially and then start coming up, right? Start coming up. Yes. Now, after the column point, it tapers to a constant value. So where the increase stopped, so it started tapering to a flat value, is where we have our equivalent point. That is the nature of the graph in this particular case. And the last thing we'll talk about would be application of conductivity in measurements. So we are saying that first one, conductivity measurements can be used as an analytical technique used to study the solubility of sparingly soluble metallic salts. The next one is that it studies the rates of reactions. And the last one, as has been determined here, it can be used to determine the endpoint or equivalent point of reaction between electrolytes. Example, acid-base reactions, as we have illustrated there. We can also use it in complexing methods and precipitations. All right, so that brings us to the end of the slide. If you have any question, kindly see any member of the ESA Academic Board. Thank you very much and all the best.